Good. So what we will do in the next less than an hour is dive a little bit back in the history of AI and just put everything into a little bit bigger context. But at the same time, we will put ourselves on a journey to a point that will lead us to large language models, deep learning, and things like that. I try to keep it non-technical, but I also along the way want to explain a little bit words that you hear, often tokens and stuff like that. Okay, so let's start with this opening slide. This is a picture I found on the internet. Aha, here's a red dot. And I'm like, oh, this looks kind of interesting. And he's like, okay, this could be like people 200 years ago would have imagined large language model training and stuff like that. And it's clearly ChatGPT generated. But there's actually a story behind it. So in 1726, so that's quite a long, it's actually 300 years ago, Jonathan Swift wrote this book, Gulliver's Travels. Have you ever heard about it? It's like with this giant and so on, with the little people, big people. So I think it's a good book. I never read it myself. So it was kind of surprising to me to see that in that book, there's a section where he travels to a land where the king had ordered an academy to develop the engine, okay? And the engine was illustrated as this, and then later became the ChatGPT image. So, and I just want to quote this one sentence, which I think is funny and weird that it exists. Everyone knew how laborious the usual method is of attaining to arts and sciences, whereas by this contrivance, the most ignorant people, at a reasonable charge and with very little bodily labor, might write books in philosophy, poetry, politics, laws, mathematics, and theology without the least assistance from genius or study. It's like a description of large language models, right? And even the picture kind of fits it a little bit. And so it's kind of fun to see that there are kind of very early ideas of this floating around. And I think it's worth looking a little bit backwards to understand a little bit better where we are today. So the longer you can look back, the farther you can look forward, which might be right or not. I'm not sure, but I will assume for the lecture it is correct. So there are several earlier books, I looked a little bit into it, that have this idea of artificial intelligence and robots in the literature. So like this book from 1872 by Sam Butler. And he essentially portrays, but like many books, was kind of a satire, a criticism of Victorian England, has this idea that out of the Industrial Revolution would grow this other species by evolution-like principles, and they would be formed then self-replicating machines and kind of obtain consciousness, okay? So that was the idea in that book. And then another, I think, thing worth knowing about is this book by a Czech writer, Karel Čapek, I hope I pronounce it right. He is the guy in this fiction book that introduces the word robot, okay? So this is, I think, the original Czech book cover, or is it English? I'm not quite sure. I think it's English. And robot actually means forced worker, which is also kind of weird. Maybe that's what we will have in our houses one day, right? And but these forced robots or forced workers in that book were actually somewhat organic. Okay, so they were not necessarily machine built. So there are these ideas floating around, probably have been for a long time. But when you look into AI history, there are a couple of points I want to kind of touch on. And you can argue whether this is really essential for AI history, but I think it shows a little bit more the context. So in the 40s, people really started, biologists, physicists started to explain how neurons work, right? And very little was known. There's an action potential. They knew this, but they started to formulate mathematical models of neuronal conduction and also neuronal processing. And these Pitts neurons are a very important one. People are still studying these models today. And so people started to think about these ideas that then later trickled down to this integrate and fire, right? Many neurons come together. The next neuron, if it gets enough juice, fires again, these kinds of pictures. So that is one background. But the mathematicians, and especially Alan Turing, also provided us with this Turing test that I already briefly talked about yesterday. Essentially the idea, can a machine imitate human behavior to a point that an expert can't tell it apart, right? So this is a Turing test by Alan Turing, a guy, by the way, who was a mathematical genius. He broke the German naval warfare code during World War II, which was to the detriment of the Nazi Germany. He later wrote a groundbreaking book in my area about the chemical basis or foundation, for the title of morphogenesis. Okay, so how is chemistry capable of producing a hand with 5 fingers, right? So how could this pattern formation kind of occur? How can zebras get their stripes and stuff like that? So interesting links to modern chemistry. And then this is something I was actually unaware of before I prepared for the bootcamp. And this is kind of a work on a very fundamental book in philosophy and mathematics, the Principia Mathematica. And it lays the foundations of mathematics at very, very simple level or basic fundamental level. For example, theorem 2.85 reads, if P leads to Q and Q leads to R, then P leads to R. Okay, these are mathematical statements. They need to be proven. I think we all feel good about it, right? But we don't have a mathematical proof really in the moment. And so already in the mid-50s, people thought, is it possibly that we can maybe build a machine that can do these simpler proofs, right? And then it came in 1956 to the Dartmouth conference, computer science conference. And one guy stole the show there, right? This Newell guy, because he had built a machine. He had, in the 50s, built a machine that could deliver these mathematical proofs. And some of them were so elegant, surprisingly, that they impressed the guy who wrote the Principia Mathematica. So we had early evidence for this kind of artificial intelligence or machine intelligence or smart machine behavior, whatever you want to call it. So the Dartmouth conference is kind of these founding events of, and I'll briefly come back to it later. But there are many other stepping stones. One is Lisp. I remember when I was a student, that was a very hot programming language, and I was very eager to learn it because it had to do with intelligence and lists that I didn't know about. I did not study in 58. Okay, just a clarification. And then these perceptrons came in, and I will talk about them in a little bit more detail. But they were also on the robotic end, again, kind of progress. So this is 1968. And let's see. This is called Shaky the robot. And this thing was navigating these rooms by itself. Okay, so it was like a self-driving Tesla, essentially, but less fast and more shaky. So you can see why it's maybe called shaky, right? This camera that was mounted on this little tower was shaking around. But it had an idea about the map of this room arrangement and the furniture in there and could move around there with some form of machine intelligence. So that's shaky. Then there were other steps like, some kind of AI toy tabletop models that required some reasoning to figure out. Then in the 70s, so there was great excitement, especially during this workshop that I had mentioned, the Dartmouth workshop. People had the feeling, wow, we just start to prove mathematical things, right? I mean, this will be great. This is a solvable problem. We can do it, right? And well, it turned out there was a period of disillusionment, and as many disillusions, they were triggered by also funding cuts. Okay, DARPA is a big funding military organization who always had an interest in this, of course. And but things bounced back, and things bounced back, and expert systems came up. And I'm not an expert on expert systems, but I'll try to explain what it is. So it's essentially you take a bunch of accountants or CPAs together in a room, and you say, hey, if a new tax return comes in, you look it over, what are you doing with this, right? And the experts are explaining how their behavior works, right? What their principle is, and then you try to formalize it. But it's not like an AI system or machine learning system. It's very regulated, right? If there's a single person filing, then I will do this. It's more like the trees that I showed you before, right? So you have this kind of flow down these kind of algorithmic trees, And they seem to be very promising, and but then kind of disappointed, right? We still surely use them today here and there, and some things have their justification, but some excitement didn't quite live up to it. And that triggered what is known as the second AI winter. And of course, DARPA immediately sensed it and also cut the funding again, right? And so we are now in the 80s. And I just mentioned the word perceptrons. So here's the idea of how I want to do this. I want to explain to you what a perceptron is. I think everyone will get it. And then I will explain what a multilayer perceptron is. And then we are kind of not that far away from modern systems, okay? So these are the stepping stones. So perceptrons were pretty much the first neural networks that really learned something. And they did this by adjusting weights, right? This would be like neural conductivity. Seems dangerous to say that. Yeah, and they are the ancestors of modern neural networks to some extent, including LLMs. So the idea is that you have input neurons, right? And you can put zeros and ones here or something like that, right? And then each neuron connects to another neuron here, an output neuron if you're, or intermediate neuron, and according to different weights. And weights are just numbers, okay? And this equation, I hope it's not too bad. You see, it's a sum over all of these neurons. And the thing that you're summing up is Wi, the ith weight, times the ith input value, right? So it might be 27 plus 1 for neuron 1, plus minus 3 times 0, or stuff like that. Okay, so this is how it goes. And you add this all up, and maybe you have a linear bias in there. And then you apply an activation to it. So this number could be large or big or negative, yeah? And then at some point, you say, okay, I'm done with my summing up business. And now I apply this function f, the activation function, to it and generate the output. In the simplest case, the output might just be 0 or 1. And this might just be distinguished between positive and negative numbers, okay? So 0 would be then false, true would be, 1 would be true. Is it soluble or not? Something like that. So that's a perceptron. Did you kind of get it? Yeah, you just do multiplication, add up, multiplication, add up. Good. So just maybe as a quick example, you could give x1 could be temperature, x2 could be white blood cell count, x3 age, x4 blood pressure, and your 0, 1 output might be infected or not, okay? Could be good or not, but this would be a possible application. The original application was in a certain ways more sophisticated because Rosenblatt took a 20 by 20 pixel image. That's low resolution, right? 20 by 20 pixel image. And he took the 20 columns or rows and stretched them out, and he had 400 pixels. So he had 400 input neurons. Do you get this, right? You dissect the image, right? Stretch it out. So that's what he did. And I'll show you a little bit how this could work. I didn't program myself. I asked Claude or ChatGPT to program it for me because I'm too lazy. And it trained this network on these 20 by 20 pixels of letters, okay? So it's a perceptron model, although it looks 2D. And here you see the letter T. And we want to give an output of 1 only if the letter that is displayed is an A, okay? You will see that frame 4 will be wrong, right? But it got 19 out of 20 frames correctly. So let's see, B, not A. Not A, that's wrong. That looks more like H. You see, you give these things in, doesn't really matter in detail, and you're trying to see whether the perceptron can tell whether it's an A or not. So it's kind of weird that this works at all, right? Because it seems so simplistic. And you can now look into the weights that you've kind of, during training, created. First of all, I have to tell you a little bit about how the training works. You essentially have a target, right? It is a letter A or not, 1 or 0. You know it. And you know what the model spits out. And you can then kind of tweak the weights accordingly at a certain rate and strength during the training to hopefully find a state of weights, set of weights that do the job that you wanted it to do. So for the 20 by 20, 400 input neuron perceptron, we can visualize them. And so you see positive and negative weight values. And of course, you start to see, because this thing is not that sophisticated, some A being encoded into that kind of memory of the network. Okay, so people were excited about it. But they were smart mathematicians, so they very quickly kind of looked at also what are the fundamental limitations here? What can I do and what can I not classify with these things? And it turns out that one thing it can't do is XOR, but I've forgotten that this slide comes first. So I just talked about this training, and it's a nice example to see how the training after a while plateaus. So these are, I have neurons from this thing that I just showed, from the perceptron. And these are the training steps, how often I tweak the W's. And you see in the beginning, there's a lot of action. For the first few hundred training steps, this network at least adjusts and possibly learns. But then after a while, well, there's really no new information stored in the network. You kind of plateau out. Okay, we will see this again. Training doesn't get better if you just keep on doing it, right? Okay, but back to the fundamental limitation. So these are logic operations. And I'm not sure these are truth tables, how familiar you guys are with it. But a 0 is false, a 1 is true, okay? And if I say false and false, that is false. But if I say true, and logic and, that's true. If I say true and false, that's false, okay? So this is how that works. And that's an OR, and that's a not that just flips it around, right? Not true is false. So these are logic operations. And an interesting one is the difference between the OR and the XOR. This is the normal, it's the OR and the exclusive OR. And the first time I learned about this was actually in introductory math in college. And the teacher pointed out the difference between our use of OR in English and German to that of mathematicians. So he said, if a mathematician comes to a quiz show, right, and wins, and the host asks the mathematician, what do you want? Do you want the sports car or this wonderful dream vacation, right? What would you pick? Car or vacation? Same value? The mathematician will pick both, exactly, because the mathematical OR is different from the exclusive OR. I'm not sure how the host will take this. You could have taken both, but you hesitated. Sorry. And so let's see. This is the car true, vacation true, everything okay situation. So this is what the mathematician perceived as the OR. But we all felt it should be the exclusive OR, right, where you can't have both, right? So not this thing here. All right. So now that you know what an XOR is, at least a little bit, that is the one thing that our perceptron, our simple perceptron, cannot resolve, because it is simple. It's a linear kind of thing. It just draws line in phase space, in input phase space, and it can kind of draw a line between the positive and negative response of an AND, an OR, and a NOT. Sorry, I have to point in a completely different direction. But the XOR you can't kind of dissect with a simple line. So that was kind of a bummer. So funny enough, these things were already running on real machines, right? And this is a historic image of them building a perceptron, right? No transistors. This was probably all tube-based and stuff like that. All right, so good. Everyone okay on the perceptron, right? So here we see that it has a limitation. We need to make it better. Here comes the multi-layer perceptron. So you have, again, on the left, our X input neurons, right? And on the right, you have one or several output neurons, right? We could have more than one. But then there are these hidden layers in between where more stuff is happening, right? Hidden, just like think of it as a black box, something goes in, something comes out. And you see all of these connections, they are now really increasing very, very quickly, right? Because not everything is connected to everything, but everything in one layer is connected to the next layer, and then again, right? And so these things, these multi-layer perceptrons, can actually function really well. But you also see already that every W, every line is a W and is a fitting parameter, right? So if you show up with your 4 data points and say, hey, 1000 parameter perceptron, please fit my data, of course it will do this, right? In some unpredictable and useless ways. So you need now more data, right, for training. That's already kind of obvious. The other thing is that the XOR problem was solved by the multi-layer perceptrons. And but there was kind of a stumbling block. People didn't quite know how to train these multi-layer networks, right? So how do you do the tweaking of the weights depending on how good the last prediction was? And that's where this concept of backpropagation that maybe some of you have heard about came in the mid-80s. This guy won the Nobel Prize 2 years ago. He's at Toronto University, old by now. And yeah, and they are the early versions of our deep learning networks. Good, so a little bit of nomenclature and some ideas. Maybe you will read about it when you read a little bit more the technical literature. So what we did in the beginning with our perceptron, do you remember this activation function F? That was just essentially a Heaviside function. If the output is below 0, negative, I make it 0. If it's above, I make it 1, right? True, false, false, true. And the problem is that didn't allow for good learning because there's no slope here. You see, there's nothing to slide down. It's flat, and then there's a jump cliff down. So people did these, whoops, didn't mean to do that at all, the rectified linear units, or ReLU. And so they don't respond like the Heaviside function. They respond in this kind of linear and then constant way. Okay? And that allows you to slide to better solutions with this backpropagation mechanism. So this is ReLU. And here's how backpropagation works. I've never explained that to a group. I should really let Gordon do this. And so here's my attempt at it. So what is backpropagation? This learning in these multi-layer perceptrons. How do these things learn? So first we do a forward pass. We put some inputs in. We let them trickle through the perceptron, through the MLP, and we get a prediction out of it. Okay, good or bad. Now we see how bad the prediction was. This is called the loss. And then we go backward through the network and we assign blame to these different components. Which one is to blame the most, okay? And then we tweak that one and hope for an improvement. And so you nudge these weights that you want to blame a little bit, and then you try it again, and then you do this millions and millions of times. And maybe the network works. Okay, so this is backpropagation. And of course, you say, how will I find out which neuron to blame, right? Or which weight to tweak? And so I have this very simple example here. So just imagine you're making a cake. And the first iteration, right? You make the cake, you try it, it's too sweet. Okay, which would, of course, to Americans not happen that often, but to us, it happens all the time. And so the final sweetness is the result. The output is the result of different components adding sweetness to the product. You have the sugar, the fruits, the cake, the frosting, right? They can all add to this. And we want to tweak it to make it a better result. So we have to bring down the sugar, but what to blame, okay? So for that, you're kind of figuring out which contributes the most to the sweet taste, right? Which is the steepest response, so to speak. And then you start tweaking there. So if the fruits barely contributed, for example, there's no big point in removing them. Yeah, you will reduce the sweetness maybe a little bit, but it's not really the most effective way. So at the end of the day, you calculate a partial derivative, a derivative of loss with respect to the weight, right? Now you have many weights. So this gets very complicated. And the mathematical concept behind it is this chain rule that you maybe already learned in high school. So there's some math, a lot of math that writes in the background. So, okay, backpropagation, we've learned that. What is softmax? Another word that you read when you read this literature. So I at least portrayed it in a way that most of these networks spit out a 0, right? And then you have maybe a lot of zeros and there's a 1 and you say, okay, infected, cat, soluble in water. But that is only one way how you can do it. It's kind of also cool if you have probabilities kicking out, right? Coming out. Like you could say, the network could say, with a 66% probability, I think the solution is A. But there is a 9% probability that it's C. You get a more differentiated output out of it, right? And the way this is done, how you take the outputs, Z, to a probability is with the softmax function. Okay? And if I look at it as a physical chemist, it reminds me a little bit of statistical thermodynamics, Eddie. So this is all kind of weirdly related to the Arrhenius equation and all kinds of things. Makes sense? So we want to also get probabilities out, right? And okay. So after we have understood all of this, and I understood all of this, this summer, I sat down, used my laptop, and I programmed a big MLP, okay? And I call it Chat Ollie. So here's Chat Ollie on my laptop. It has 8,000 input neurons, one hidden layer, so one hidden layer only, 512 ReLU neurons, and 160 output neurons, okay? So that's what I programmed with the help of ChatGPT or whatever I used. Okay, so this means that we have a lot of weights to consider, right, in this network. And we have these little plus B that you might or might not remember. Those we have also several of them. So we have in this Chat Ollie thing for over 4 million parameters to tweak, okay? Compare that to fitting a straight line. So 4 million parameters to fit. So what did I actually try to accomplish? And I admit I was naive, optimistic, let's say. So I downloaded a big general, oh no, was it organic? No, I think it was general chemistry textbook, right? There's this free textbooks, they're very, very nice. The textbook, I didn't care much about, had 2.5 million characters. This is what I cared about, right? And I wanted to train Chat Ollie on that textbook. So what I did is I took 50 consecutive characters from the text and I converted it to a number. So these formed essentially my input neurons. The book turned out to have 160 different characters, hyphens, commas, colons, right? All kinds of weird stuff. So this kind of ended up in my input neurons. The output also ended up in output neurons that were supposed to predict the next letter, okay? And then I read the softmax that you learned about, and I ran backpropagation that you learned about, and an epoch for the training means I went one time completely through the book, okay? I shifted my window through the book, the computer did, and it saw the whole book once and adjusted the weights. Good. So the idea was to predict the next letter. I typed something in, not from the book. I typed something in, and that Chat Ollie thing predicts the next letter, and then moves on like a chatbot producing the output. Another thing that is important that you as normal ChatGPT users don't see, these models have temperatures, okay? And the temperatures have something to do with how reliably it picks the output A with the 90%, right? You want to have that output most of the time, but maybe sometimes you want to have a slightly different result. So you can dial up the temperature of the model. It's not a real temperature. And then it might also take the 10% probability occasionally. Good. So that's the temperature in these models. So low temperature means it plays it very safe. High temperature, it gets a little wild. Okay. So I ran this only half a T equals 0.4 for half an hour, yes. Mm-hmm. And the temperature was, for this time, the temperature was set to 0.4. Usual range is 0 to 1. And I prompted Chat Ollie with salts usually involve metallic cations and, now comes the disappointment, and the substance and the silicent in the reaction, the molecule and oxide in the concentration of a solution of molecular formula and sulfur molecule. What the hell, right? And you might say, oh, complete failure. But man, it learned words, all right? It didn't know any words in the beginning. I could have as well trained it on, maybe not Chinese, but German. And so, okay. So it learned some chemistry-related words from that chemistry book, okay, in one epoch, one time through the book. Then I did it again 15 times overnight. And I remember how I woke up the next morning and I was excited. And I thought I would have trained this ingenious thing. Salts usually involve metallic cations, and the sum shown the rate of the elements of the two formed the orbital various. Like it didn't even improve, right? But then you look a little bit more carefully. Look, it learned punctuation that you continue with a big letter, right? So it had picked up more stuff in these 15 things. And of course, the next question would be like, what if I run it a week, right? Probably my laptop would melt, right? But disregarding that, I looked at the training loss. And you remember we introduced this as a function of epochs. How often did it go through the book, okay? And you see it plateaus, right? I could have squeezed out a little bit more from that network, but I was kind of done with it. I think I kind of plateaued. It would have not been particularly helpful to run it much longer, right? So why was this such a failure? Okay, you're probably all disappointed as I was, right? Why the heck am I even showing this? So why was it such a failure? Well, Chat-Ollie has 4 million weights. ChatGPT-4, older model, 1.8 trillion, okay? I trained Chat-Ollie on one textbook. ChatGPT is trained on much of the internet. I had a laptop, and one night, I don't know how long these things were trained, but they have, oh, well, I do know, 25,000 GPUs, 3 months, $100 million, okay? Bit of a difference. Moreover, Chat-Ollie, the MLP, the multilayer perceptron, is not a generative pre-trained transformer. That was another advancement, right? The introduction of transformers that brought us to where we are now. So how could this possibly all work? How does the stuff start, right? In Chat-Ollie only predicted the next letter, right? It had a little 50-character window and predicted the next letter. So I think we can all do this. I bought this toaster and, all right, we can guess this. I bought this toaster and I'm unhappy, right? We can guess these next letters pretty well. And, but then, you know, this is essentially how these models were trained. Next letter walks out, you get a good word, like I got good words with Chat-Ollie. But then things get more and more mysterious. And at some point, and by the way, back then they trained a lot on Amazon reviews, as far as I know. At some point, a new quality kind of arose, right? Because if I'm saying, I bought this toaster and I'm unhappy because the toast burns, and now I want my money back, question mark, how do you continue, right? So the qualitative change was that the systems, the models start to understand whether it's a positive or negative review, right? They would have not said, and I would buy 10 more. They could have said that it's linguistically correct, but they had kind of figured out this is kind of a negative review. I should continue it in that spirit, okay? Really weird when you think about it, right? It went from next character prediction to like, yeah, kind of get the idea of this review. Strange. Okay, so we go from syntax to semantics to pragmatics, potentially. So this is one of the open co-founders of OpenAI, and I want to just play this little video.
While more accurate prediction of the next word leads to more understanding, real understanding. Let's consider an example. Say you read a detective novel. It's like it's complicated, large storyline, deeper characters, lots of events, mysteries like clues. It's unclear. Then, let's say that at the last page of the book, the detective has gathered all the clues, gathered all the people, and saying, okay, I'm going to reveal the identity of whoever committed the crime. And that person's name is...
Predict that word.
Predict that word,
Yeah.
exactly.
My goodness.
Right?
Yeah, right.
Now.
So, right, I mean, I think we would all agree, if the system can predict that name, it has it's established without a rigorous definition of understanding, some level of understanding, right, of what the book was all about. It did not spit out just the next character. All right, so I always said character and word and stuff like that, but we heard this word before. what they are doing is next token prediction, right? So here's a little bit on this token business for GPT-5. And so here you can go to the webpage and play with it yourself. It's from OpenAI. So this is called a tokenizer. You type in a sentence, right, or a long word, or if I remember correctly, to study. And it translates it into what ChatGPT really sees. So you see, most of the tokens, the different color blocks, are indeed words, right? But when you look at the German wonderful word Oberwieser Dampfschifffahrtsgesellschaft, it's not in the dictionary, so it breaks it into different tokens, okay? The Chinese word, for example, was a single token, although it has 2 characters, or whatever these things are called. And so what ChatGPT sees is never your text. This is also kind of a shocking realization, right? You type something in, it feels kind of cool. There's a tokenizer in the front, and it transfers them into numbers, okay? And you see the numbers can get quite high. Like the word learning is the token 54,609, okay? And GPT-5 knows about 20 different token IDs, okay? So it never sees a word of English language, really. It sees these numbers. And as a rule of thumb, if you forget everything, it's roughly a word, okay? But occasionally a little bit different. So continuing along this history story, you remember that lady? She gave this end video where she talked about AI and education, Fei-Fei Li. She actually became quite famous with this ImageNet. And that was the first time the idea that we want many, many, many different images and train AI on those images. This is now 2009. So she combined with other people this really large ImageNet database. Okay, and then wish I could get this go away. There were other stops like AlexNet and then generative networks. The moment where AlphaGo, we saw Elias talk about it, first one against a human, Grandmaster or whatever they're called. And then Google Translate, and I remember that very vividly. You're probably a little too young. But I remember we had automatic Google translation tools. They were kind of cool, but often very funny, right? Because certain things were just like off, right? And then there was this one moment, it was suddenly good, when deep learning kind of was injected into this thing. All right, so history accelerates. Transformers, I will talk about them a little bit, or I'll show you a video in a second. And then in around 2018, this whole large language model race started. And as a rough idea, doubled every 4 months. GPT-3 came out. AlphaFold 2 cracks protein folding problem. If you ever want to talk with Wei about this, it's kind of interesting. He, for years, competed in these competitions to predict protein structure. And suddenly this came out. Does it even still exist, the competition? Okay, but it has changed a lot. Okay, then ChatGPT 2022, that's probably when many of us first got aware of it. Open source models come out, very interesting thing, Nobel Prizes, and then the major investment, right? And you see how things are skyrocketing and companies get rich, stockholders get rich, I guess. And I think the one thing that's important to realize is this idea of scaling. If you can figure something out that can be scaled, you're probably making a lot of money and impact. And the scaling idea that they figured out is that if I take some data and I take more compute, more data centers, I can make it better in a predictable way, right? I don't gamble this. I have a very clear path forward how to make this better and make more money with it. Well, I don't know how they make money. So these are kind of things to keep in mind. And I want to show you this here. Well, some titles. That explains, I think, Transformers better than I could. So I just stole it from this webpage and the YouTube and will play it to you.
You mentioned that the interlevel piece of a transformer. This is one of the key pieces of technology inside large language models and a lot of other tools in the modern wave of AI. It first hit the scene in a now famous 2017 paper called Attention is All You Need. And in this chapter, you and I will dig into what this attention mechanism is, visualizing how it processes data. As a quick recap, here's the important context I want you to have in mind.
The goal of the model that you and I are studying is to take in a piece of text and predict what word comes next. The input text is broken up into little pieces that we call tokens, and these are very often words or pieces of words. But just to make the examples in this video easier for you and me to think about, let's simplify by pretending the tokens are always just words. The first step in a transformer is to associate each token with a high-dimensional vector, what we call its embedding. Now, the most important idea I want you to have in mind is how directions in this high-dimensional space of all possible embeddings can correspond with semantic meaning. In the last chapter, we saw an example for how direction can correspond to gender, in the sense that adding a certain step in this space can take you from the embedding of a masculine noun to the embedding of the corresponding feminine noun. That's just one example. You could imagine how many other directions in this high-dimensional space could correspond to numerous other aspects of a word's meaning. The aim of a transformer is to progressively adjust these embeddings so that they don't merely encode an individual word, but instead they bake in some much richer contextual meaning. I should say up front that a lot of people find the attention mechanism, this key piece in a transformer, very confusing. So don't worry if it takes some time for things to sink in. I think that before we dive into the computational details of all the matrix multiplications, it's worth thinking about a couple examples for the kind of behavior that we want the attention to enable. Consider the phrase.
Oh, sorry. Oh, suddenly very quiet. Would love to get this all.
C of the mole. You and I know that the word mole has different meanings in each one of these based on the context. But after the first step of a transformer, the one that breaks up the text that associates each token with a vector, the vector that's associated with mole would be the same in all three of these cases, because this initial token embedding is effectively a lookup table with no reference to the context. It's only in the next step of the transformer that the surrounding embeddings have the chance to pass information into this one. The picture you might have in mind is that there are multiple distinct directions in this embedding space, encoding the multiple distinct meanings of the word mole, and that a well-trained attention block calculates what you need to add to the generic embedding to move it to one of these more specific directions as a function of the context. To take another example, consider the embedding of the word tablet. This is presumably some very generic, non-specific direction in the space associated with lots of other large, tall nouns. If this word was immediately preceded by Eiffel, you could imagine wanting the mechanism to update this vector so that it points in a direction that more specifically encodes the Eiffel Tower, maybe correlated with vectors associated with Paris and France and things made of steel. If it was also preceded by the word miniature, then the vector should be updated even further so that it no longer correlates with large, tall things. More generally than just refining the meaning of a word, the attention block allows the model to move information encoded in one embedding to that of another, potentially ones that are quite far away, and potentially with information that's much richer than just a single word. What we saw in the last chapter was how after all of the vectors flow through the network, including many different attention blocks, the computation that you perform to produce a prediction of the next token is entirely a function of the last vector in the sequence. So imagine, for example, that the text you input is most of an entire mystery novel, all the way up to a point near the end, which reads, "Therefore the murderer was." If the model is going to accurately predict the next word, that final vector in the sequence, which began its life simply embedding the word "was," will have to have been updated by all of the attention blocks to represent much more than any individual word, somehow encoding all of the information from the full context window that's relevant to predicting the next word. To step through the computations, though, let's take a much simpler example. Imagine that the input includes the phrase, "A fluffy blue creature roamed the verdant forest." And for the moment, suppose that the only type of update that we care about is having the adjectives adjust the meanings of their corresponding nouns. What I'm about to describe is what we would call a single head of attention, and later we will see how the attention block consists of many different heads run in parallel. Again, the initial embedding for each word is some high-dimensional vector that only...
Yeah. The sequence of videos, I think they're awesome, if you want to understand this.
First time I've learned that it actually doesn't look at the words itself, but I've noticed that when I type, let's say in Gemini, isolate typos, but it understands what the word is. So how does it have
That's a very good question. I don't have the answer. We can ask Gordon later. He has 10 minutes to figure it out. I really don't know. But so let's just digest this for a second. So we have data centers, we have computers, we have nanotechnology where we arrange atoms. We have this crazy software running on it. So when you think about this, whatever the consequences of it is, we created something amazing, right? Something that is unimaginable, I think. All right. Oh, it's stuck. Let me unstuck it. That's very strange. Maybe you have to play it to the end.
In the last chapter, you and I started with step 2.
Oh, okay, good. We are back in business. So I would just want to complete this quickly with some other comments. So these are the guys from the Dartmouth workshop that I had mentioned. And for them, it was very natural, when you think about the history line, to think of this as an analogy to biology and the human brain, whether true or not. So I want to put a little bit comments on this. So there are similarities and there are differences. One similarity is if you mess up one of these weights in a big network, probably doesn't make much of a difference, okay? And if I destroy one of the neurons by drinking too much beer tonight, or maybe more than one, I will not wake up and have forgotten one memory or two memories. It's not like the memory is stored in one neuron. It's holographically stored. And if you waste some of your neurons, right, or you just age, you have fewer neurons, that memory doesn't disappear one by one. It's all getting a little more fuzzy, okay, and the performance gets a little bit down. So that's kind of this holographic aspect of it. Then they're kind of interesting, and I'll show you a picture, similarities to how we process with our eyes, right? It's not like all done by the brain. There's all this neuronal tissue in between that does a lot of pre-processing for us. And well, I guess both are error-driven, right? I once read that people were saying that the evolutionary function of our brains is to minimize surprise, okay? If you're never surprised, you're probably cool, right? But if the tiger surprises you, it's probably the end. And all of that gets a little fuzzy. There are also differences. So humans are very good at one-shot learning, right? These are old German characters. And I think if we were to look at them for a little bit, right, although you have only 3 samples, and then I would show you others, you would have a good chance in picking it out, right? I didn't present you 1 million pictures of this symbol, right? So we are very good at one-shot learning. A more trivial thing is if you show a kid a giraffe or dinosaur, it will probably be able to see a week later dinosaurs and say dinosaur, right? Good. Then a big difference is we have a body, right? And I think I talked with Sean, see here, about this earlier. That makes us, at least in the moment, different. How robotics will change this, and I do not know. But for us, it means something if we say heavy, right? Beyond the word and associations. And well, we continuously learn. I hope a little bit of it is happening in the moment. And networks are kind of more this frozen thing, never mind the context window. And then you train it again and you get a new model out of it. So that's very different. They can just be off more easily. But there are these intriguing similarities between neurons and these nodes that I showed you, right? We have a network in our head of neurons, interconnected neurons, and they've depending on who you listen to, integrate and fire or do more complicated information processing. But there's some similarity and yes, also differences there. And this is the part of our retina, right? And you see when you look at how the neurons are connected, these are neurons who can pick up vertical lines, horizontal lines, motion. You have more motion detectors here, right? In the peripheral view, it doesn't look that much different from a neural network that I showed you. So there's similarities. Okay, so I give you one example of that. I hope this works. I have astigmatism. Wen tells me it works. Do you see in this optical illusion these gray spots? Yes. This is because the neurons in your eye are locally inhibited, right? Because there's more bright, so they start to inhibit this spot, and you start to see these phantom gray spots. Who sees the gray spot? Who doesn't? Well, we should form a team. We should form a team. I have a hard time with it. Okay, so there are similarities of neurons inhibiting each neighbors, close neighbors with negative weights. Yeah. And the crazy thing is we've started, not me personally, we scientists have started to map the brains of smaller animals. So this Drosophila fruit fly, it's called the connectosome, published 2 years ago. We have all the neuron connections, right? We can run models in it. And it doesn't work very well. Even for simpler animals like worms, it doesn't work well. There seems to be something else. But when you're on Twitter, you see people who put, without much respect, neural models, models onto these networks, the geometry, the connection, and they claim that they can get fly response out of these things. I personally don't believe it, but the idea alone is already crazy, right? Like rooming, stuff like that. So since we talk about the brain at this end again, another Nobel Prize winner in 24 was Hopfield, and he had a different type of network. I only want to briefly, I'm running out of time, mention it. So in these networks, all neurons, mathematical networks, all neurons are connected to all other neurons, okay? And in this very high, complicated, high-dimensional weight space that arises out of it, with different learning routes, the memories are stored as local minima, okay? So this is a 3D representation, but in reality, this is like a gazillion dimensional representation. And there are like low spots in there. We can't really imagine it. So let's stick with 3D. And this might be the memory of the letter A, okay? The sound of an A, right? This might be the sound of an E, right? And I find this so amazing. If I try to imitate some of Wen's Chinese pronunciation, she gets always very anxious about this. I don't know why. I can hear it for a second. I think I can stabilize it, right? But it's like me holding, I don't have a minimum there. She has a minimum, right? So I'm kind of very hard trying to stabilize my point there. But if I wait a moment, I'm sliding back to a German A or something like that. So it's weird to think about it like that, right? Okay, so that's maybe my last slide. I think we are all wondering, what does it mean to think and to understand, right? And this is a nice quote, well known. The question of whether computers can think is like the question of whether submarines can swim, okay? It's probably not a valid question to ask, but we are all tempted to do it.